Talking on, what was it, Saturday? I think so. We were talking on Saturday about proof objects, and this is a very familiar topic from last week, so I'm not going to hammer on it too much today, but there are a few more things to say. So let's quickly review. Last time we looked at some proof objects that are generated as Calc interprets tactic scripts. And then we observed that proof objects are real data. So the Curry-Howard isomorphism is not some imaginary thing. It says proofs are really data structures, and you can do computational things with them. You can apply proofs of implications because they're just functions. If you have a derivation tree, well, that's just a data structure, and you can do things like investigate what's in it and do case analysis on what rule was used to do the final step, or even do induction over the whole thing. And this is a completely familiar thing from the kind of proofs that we do informally in programming languages. This is proof by induction on derivations. And then the last thing we discussed was this kind of trade-off between computational definitions and inductive definitions of certain concepts. And the observation was that for some concepts, there's a choice, and kind of either way works, and in fact it's often useful to do it both ways and show that they're equivalent, because then you can have the benefits of both for the modest extra cost of an equivalence proof. But however, that for some concepts only the inductive proof really works because it's awkward or impossible to fit the natural definition of that concept into a obviously terminating computational presentation. Here's one last thing we can do with evidence. We can do inversion on it, and this is also something that we often do in the kind of proofs that come up in meta theory of programming languages and logics, which is you have some inductively defined relation, like a typing relation or an operational semantics. And you want to do a proof of the form, if such and such is typable, then blah, blah. And the way you do the proof is you say, well, consider all the possible ways that there would have been of proving that that was typable. And now for each of those possible ways, blah, blah holds. So this often comes up, for example, if you're doing an inductive proof where you need to walk over two things. So you have maybe a typing derivation and a derivation that one term steps to another. So you have for those of you who've ever done proofs about, say, simply typed lambda calculus, if you haven't, we'll get to them, but this is just a little preview for those of you that have seen it. Often proofs will be of the form, suppose we have a term and it's typable and it takes a step. So we have now two derivations, one in the typing relation and one in the takes a step relation. Those relations are both inductively defined. So in order to do the proof, we often have to kind of take apart the derivations in lockstep. So we do that by doing induction on one of them, and then for each case of that induction, we need to look at what the possible shapes of the other one are. And this looking at the possible shapes of the other one, kind of tearing it apart to find the substructures that correspond to the substructures of the one that we're tearing apart inductively. This is in a paper proof, you will informally often say, by examining the rules of the definition, we see that the only possibilities are A, B, and C. Or if you want to be a little bit more pedantic, or if your definition is a little bit more complicated, you may actually prove a lemma that says the only possible ways of showing that say a typing derivation of a fact of this form could exist are A, B, and C. So let me say that more clearly. One often proves so-called inversion lemmas, which say, if I have a derivation of typing and the type involved has this form, then only these two rules could have been used to prove it. Those are called inversion lemmas. And the inversion tactic is named that way because it's doing effectively the same thing. It's, we saw it first for use only with equality statements, but actually it does something much more general. It says, take a fact, take a hypothesis, whose type is some inductively defined proposition, for example, equality, but other ones as well, evenness, beautiful, gorgeous, typing relation, whatever. And consider all the possible ways that that fact could have been established by applying a constructor to some data, and generate subgoals for each one. Okay, so here, for example, is a little. Let's go to our Coq window and actually look at this. No, that's not the one I want to look at. Right, so suppose we want to show that if n plus 2 is even, then n is even. How do we do that? Well, we have a derivation by assumption that says n plus 2 is even. And basically what we want to do is say, well, consider how that derivation could have been built. It's a data structure. How could we possibly have put together constructors to build something of that type? So we do that with inversion, and the inversion, as we've seen before, gives us some equalities, things that must have been the case, things that must have been the same in order to correctly apply that constructor. In this case, not a very interesting equality. It just says that n must have been even where, let's see. Actually, I'll show you another trick right now. The problem with inversion is a very powerful tactic. It's useful in many situations, but it has one drawback, which is it tends to generate a big pile of equalities that you don't really understand. So the thing that I almost always do immediately after inversion is to substitute away all of the equalities. And I forget whether we've discussed this one in detail, but there's a tactic called subst that takes all of the equalities in the context where one side is just a variable and rewrites it away. So inversion followed by subst will in some way deal with all of the equalities that get generated. Often the equalities are between two variables, and then it just chooses one. So you can't necessarily quite predict what the names are going to be in what comes out. But what comes out is generally so much simpler that you don't care. So here, well, basically it's reduced what we need to show to something trivial. See, is that all I want to say about this? I think that's all I want to say about this. The point is, inversion takes a piece of evidence and figures out all the possible ways that could have been built. Sometimes, if the evidence is contradictory, if it's something that isn't actually provable, then as we've seen, it will generate 0 subgoals and immediately prove the goal. Or sometimes, if there are several ways, it will generate several subgoals. In the process, it generates a bunch of equalities, which can be, if you don't want to try to figure them out laboriously, can be dealt with all at once by subst. Okay? So canonical forms lemmas usually get, that term usually gets applied to a slightly different kind of lemma. It's a similar thing, but but it's a little bit more than just look at the ways that this could have been built. It's knowing something about the, well, let's see. Yeah, okay, they're very close relatives to a first and second approximation of the same. The reason I'm hesitating is that inversion lemmas are usually easy to prove just by kind of looking at the definition. Whereas canonical forms lemmas are usually deeper properties of the system. Other questions? Okay, new topic, slightly new topic. Propositions themselves, not just the proofs of propositions, but propositions themselves are data structures. And they are things that we can program with. So Coq is very orthogonal in this sense. And so, for example, you can write a function that walks over a list and in some way calculates a proposition. For example, you could have maybe a list of propositions, and you could write a function that folds over the list and forms the proposition that is their conjunction. That's a perfectly sensible thing to do. And in many situations, I hope we'll have time to talk about this, in many situations where you're kind of driving Coq hard, it can be incredibly useful and convenient to not just kind of write down a constant proposition and then try to find proofs of it, but to actually calculate the proposition that you want to prove in a computational way. Okay, so one thing is, it's incredibly important, although I hope this is kind of an obvious point for you, it's incredibly important to keep the distinction between a proposition and a provable proposition. So a proposition is just a claim, and that claim may be either provable or not provable. So for example, 2 + 2 = 4 is a proposition. 2 + 2 = 5 is also a proposition. And so they're both perfectly good propositions. The only difference between them is that one is inhabited and the other is not. Propositions are ordinary data in Coq, of course, at a kind of different level than the data that is the proofs of propositions. But all the same things can be done with them. So we can give names to propositions. So we can, for example, define a name plus fact for the proposition 2 + 2 = 4. And then we can write a theorem that says whose body is, whose type is, if you want, plus fact. Okay, now we can construct we can use old propositions to build new propositions. We've seen this before, of course, because you can take two propositions and put an arrow between them, and that's a new proposition. But we can also define parameterized propositions like even. So that's a function from numbers to propositions. We can define multi-argument propositions, and we can define higher order propositions. So for example, here are a couple of propositions. Here are a couple of parameterized propositions parameterized on other propositions that might look familiar to you. So this proposition says, this parameterized proposition has one instance for each p, where p is a property of numbers, a proposition parameterized on numbers. So for each property of numbers, true for all numbers p is a proposition, which is true informally or provable exactly when for all n p of n is provable. Okay? All right, last thing in this chapter is induction principles. So, of course, the thing that we were looking at a second ago is a little piece of the induction principle for natural numbers. And indeed, the induction principle for natural numbers is nothing very different from the rest of what we've been looking at. It's just a proposition. In fact, it's this proposition. It says, for all p, if we have a proof of p of the zero instance of p, and if given a proof for the n instance of p, we can build a proof for the n plus 1 instance of p, then p holds for all numbers. Okay, so this is the standard induction principle for natural numbers. And the way Coq works is that when you give an inductive definition, it will automatically generate this induction principle and a couple of other closely related ones. So effectively, this induction principle is an axiom that is generated by the inductive definition. So when you give an inductive definition, what gets defined is the constructors, which are axiomatic evidence for building elements of the inductive type, plus this thing, which is an axiomatic way of pulling apart, an axiomatic eliminator, if you want, for the inductive type. And what that means is that if you want, you can actually get away without using the induction tactic. The induction tactic is just apply of the induction principle. It's doing a little bit more. The induction tactic is doing a tiny bit of bookkeeping about kind of rearranging quantifiers for you. But essentially, all that it's doing is the core of what it's doing is just apply of the induction tactic. So this proof illustrates that by proving a simple fact about multiplication without using the induction tactic, simply by doing apply nat end. And if you work through this proof, you'll see that it's slightly different. It differs in a few details because nat end is slightly lower level than the induction tactic. But basically, it's exactly the same thing going on. Okay, and now I don't want to spend a long time talking about this because there are some details to internalize that are a little bit tricky. It's better to take it offline and just read about it and experiment a little bit yourself. But just to give you a high-level overview, the induction principle that's generated by the inductive definition, of course, corresponds to the inductive definition very closely. So essentially what happens is your inductive definition has several constructors. The induction principle has one hypothesis for each of those constructors. And each of the hypotheses says, okay, given some induction hypotheses, prove a particular case of the proposition that we're proving inductively for that constructor. Okay, so we have a bunch of constructors for each one. So for a given constructor C, it takes some arguments. Some of those arguments will be instances of the same inductive type. Right? So for example, with the list constructor, with the list inductively defined type, the cons constructor takes two arguments. One is a number, the other is a list. So the clause, the row in that type for the cons constructor will be of the form, suppose I give you a number and a list, and a proof that your property holds of that list. Okay, so the and a proof that your property holds of will come along with every one of the arguments to the constructor that has the inductive type. So you don't get it for the number, you do get it for the list. And then you're supposed to show that for that constructor, if we use that constructor to build a new list out of that number and that sublist, then it has the property that we're trying to show. So knowing that, that was high level, and you'll need to read it to fully internalize it probably, but at a high level, knowing just the form of the inductive definition, you can read off the induction principle in a very direct way. And vice versa. Given the induction principle, you can go back to the inductive definition. Okay. Any questions? So let's go on then to the next chapter, which is called Logic. And let's look at how the very low-level built-in facilities of Coq can be used to define familiar logical connectives. So the connectives that we've used so far have been basically implication, quantification, and equality. It turns out that equality is definable. We kind of already know that, but we'll see it in detail here. So equality is definable, so that just leaves implication and quantification, which turn out to be the same thing. Right? So both the arrow and the for all are instances of pi types. And indeed the way the arrow is simply syntactic sugar for the special case of the pi where it's non-dependent. Okay, so here's the same silly proposition written three different ways. So the last way is the most natural way, which says if n is beautiful, then n plus 3 is. Notice that intuitively, this piece of evidence is a two-argument function. It takes n, and it takes a piece of evidence that n is beautiful, and it returns evidence that n plus 3 is beautiful. So we could name this evidence. We're not going to use that name on the right-hand side here. We use the name n, but we don't use the name of this evidence in the type of the returned evidence. So, but we could still give it a name. We could call it E, for example. Or we could use the special underscore kind of pseudo-identifier that says, I'm binding a variable here, but I don't care to give it a name because I don't need to use it later. Okay. Important point. We are, of course, using the evidence for beautiful n. We're using the value that's going to be passed here in constructing the value that we return. But the type, but the evidence, the value itself, doesn't occur in the type of the returned evidence. So that's why we don't need it here. Okay, so the non-dependent case of for all is just arrow. And for all is just a notation for pi. So we only have pi.
So what rules are there? Pi introduction, pi elimination, and
The usual pi rules. Yeah. Okay, so how could we define other connectives? Well, here's conjunction. It's pretty simple. Conjunction is an inductively defined type. So given P and Q, and PQ is a proposition with one constructor, conj, which takes evidence for P and evidence for Q and becomes or yields a data structure that counts as evidence for P and Q. And we can introduce familiar syntax in the usual way. And now we can prove things about conjunctions using no extra tactics. So we don't need to introduce any more tactics for dealing with conjunctions. As a convenience, I will introduce one more tactic, which is I find it a little bit annoying to have to remember that the single constructor of the conjunction of the and proposition is called conj. So rather than remember that and say apply conj all the time, I usually write just split. Right, so split says I'm trying to prove a conjunctive proposition. I'm trying to prove P and Q. Split says break it into two subgoals, one for P, one for Q. And split is nothing more than a synonym for apply conj. And then conversely, if I have a conjunctive hypothesis, I can split it apart into two hypotheses, P and Q, by using inversion. Okay, so inversion is your friend in many of these situations where you have inductively constructed evidence and you need to find out how it could have been constructed. That's exactly what we need here. So you say inversion and it gets pulled apart into separate hypotheses for the evidence that must have gone into building the evidence of P and Q. So let's actually do this little proof. Called. So let's show that and is commutative. And let's do it together. So how shall we start? Intros, good way to start almost anything. Okay, so we have P, Q, and we have propositions P and Q, and we have the hypothesis that P and Q holds. So inversion would be a good way to get the juice out of the hypothesis that we have. So inversion H splits H, so keeps H, but also dumps into the hypotheses the evidence that must have been used to construct H. So we have now P and Q. And now what? Split will give us two subgoals, one for P, one for Q. One for Q, one for P, because we're trying to prove Q and P. And now, apply something. Apply, let's see, we want Q here, so apply H1. That gave us Q, and then apply H0 gives us P, and we're done. Yes. Yeah, so there's I'll show this later on, but since it's come up now, oops. Oh, Philly, come on. There we are. Okay, so if you know that the thing that you're trying to prove is a local hypothesis, you can just say assumption and not bother giving its name. All right, going on. If and only if is just P implies Q and Q implies P. The rest of Software Foundations doesn't make very heavy use of if and only if because in older versions of Coq, if and only if hypotheses were a little bit awkward to work with. So Coq wasn't good at, for example, you couldn't just take an if and only if hypothesis and apply it, and Coq would have to figure out which direction to apply. It's gotten much better, so we're gradually reintroducing more uses of if and only if. You may want to use it more than we do. Okay, what about disjunction? Well, disjunction is an inductively defined proposition with two constructors. There are two ways of proving P or Q, either give evidence for P or give evidence for Q. So there are two constructors, one that takes evidence for P and one that takes evidence for Q. And now the rest of the story is kind of what you would expect. And once again, it's a little bit annoying to have to remember the names of the constructors, which are or underscore intro L and or underscore intro R. Those are the names that the standard library writers decided on. I don't like having to remember those, so I usually use left and right as shorthands. So left is a shorthand for apply intro L, which says intuitively, I'm trying to prove a disjunction. Left says, I want to prove the left disjunct. So to prove, my goal is P or Q. I'm going to satisfy that by proving P. Falsehood is representable in Coq in a particularly trivial way. So this is an inductively defined proposition. It looks funny, but it's a perfectly legal one. It has 0 constructors.